Now that we are done discussing about the introduction of carbohydrates, including their nomenclature, their types, their isomerisms, and the way that ring closures are formed, let's go a little bit within the realm of reactivity. And so here we have the general reactions of carbohydrates, specifically redox and glycosidic linkage. And as you will see, these are all monosaccharides, alright, but some examples such as these are disaccharides, and I'll explain why later. They also exist in either linear or cyclic forms because they have certain points that I would like to mention later on with regards to the reactions, alright, and the properties of the carbohydrates after or during reactions. So anyway, let's start. I would start by showing again or recalling the functional groups present in carbohydrates. Again, we have three. We have the formal group, we have the hydroxyl group, and the one which is not present here is a keto group. And the formyl and the keto groups are more oxidized as compared to the hydroxyl groups, so that if you oxidize a hydroxyl, it could become a formyl group or a keto group. And if you have a formyl group, if you further oxidize that, it will become a carboxyl group, and vice versa. If you reduce a formyl or a keto group, you will end up with a hydroxyl group. Alright, so to cut the chase, we'll go directly to the reaction so I could further show you in a clearer fashion what I want to express. So here we have reduction. This one in particular is obviously an aldose. It has a formyl group. This is again glucose, guys. Alright, so if you reduce this using a hydride such as lithium aluminum hydride, so if you reduce this, what you're going to target actually is the one here, the functional group in this carbohydrate, which is the most oxidized at the moment. Alright, because what's the point of reducing something which is more reduced than another functional group? So you want to target the more oxidized part of this one. And between hydroxyl and formyl, of course, what we're going to target is the formyl group. It's the more oxidized portion. So as to say that, again, upon reduction of a formyl group, we now have a hydroxyl group, particularly a primary alcohol group. Alright, and the name of this one, alright, in general is an alditol, because it now becomes simply an alcohol with many hydroxyl groups. In fact, here we have 1, 2, 3, 4, 5, 6 hydroxyl groups, alright. And if it came from glucose, then specifically the name of this one is glucitol, alright, glucitol. And if you're kind of interested, if it has another name, the name of that compound is also known as sorbitol. But there's also another way by which you could reduce particular sugar. Alright, instead of simply reducing the formyl or the carbonyl group, if it is the case of a ketose, you could actually remove an actual oxygen here. You could remove an actual oxygen. For example, we want to target carbon number 3. We assume that this is OH, right? But after the reaction, let's say it becomes, you retain this, okay? You retain all others, then this one becomes H. So if previously you had OH, okay, and you're left with H, basically you removed the oxygen from there. That's why if we have here a sugar, alright, you could also name this one as a deoxy sugar. In particular, this would be, if this is carbon number 1, 2, 3, carbon number 3, this is 3-deoxy glucose, to be very specific. Actually, a famous deoxy sugar is something that we have already encountered, and just to, I think you're already getting the hint of what that is. This is a 5-carbon sugar known in nucleic acids known as ribose, and I think you guys know where this is going. Alright, if you target one hydroxyl group there, particularly at carbon number 2, this is carbon number 1, this is carbon number 2, so this is our target. This one is our target here, 3, 4, carbon number 5. We target carbon number 2 and we remove the oxygen here. We come up with 2-deoxyribose, the deoxy sugar present in DNA. Alright, so that's it for reduction. Now, how about for oxidation? I'm going to add a divider so that it would become less confusing. So again, I have here glucose, which is an aldose. Oxidation can happen in 3 ways, depending on the reagent. If you use a weak oxidizing agent, such as cupric ions or copper positive 2, what would happen is that the easiest part here, which will be oxidized, is the one which is more oxidized, because it would take a little more effort instead of putting much energy to something that is less oxidized. Alright, the same case with here. Alright, here the explanation is, why do you have to reduce something which is already reduced? Here, why do you have to oxidize something that is reduced? You can oxidize instead something which is already partially oxidized, and in the battle for oxidation state between a formal group and the hydroxyl group, obviously the formal wins. So when you oxidize this part, the formal group would get oxidized first. So in short, everything here would remain except the formal group, and the only thing that it would become after oxidation is COOH, which is the carboxyl group. And again, everything becomes unchanged. So now, we have an acid, right? Specifically, the name of this acid in general is an aldonic acid. And if it came from glucose, specifically, the name of this aldonic acid is gluconic acid. Have you encountered the ferrous gluconate? Alright, this is the gluconate that exists in that particular iron supplement. Now, if you use a stronger oxidizing agent, alright, a stronger oxidizing agent, such as nitric acid, now in addition to the formal group, obviously here, this one will also encounter the same fate, or will also have the same fate as this. But in addition to the formal group, we target another group. Alright, and if you ask what is that, the first answer is definitely not everything will become carboxyl. So we have here OHs, right? OH, 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 OH. But the 4 I have just drawn are secondary alcohol groups. The one here at the end is a primary alcohol group. And when you talk about protection, the primary alcohol group is less protected by carbons as compared to the secondary, obviously, because there are more carbons shielding these hydroxyl groups right here. So meaning, in short, in addition to the formal group, if you use a strong oxidizing agent, you also oxidize this terminal portion. So instead of having just one carboxyl group, you now have 2. And everything else remains unchanged. All the secondary alcohol groups do not react even with a strong oxidizing agent. The specific name of this one is an aldaric acid. And in particular, the name of this aldaric acid is glucaric acid. Alright? Now, finally, you could also use a strong oxidizing agent again. But this time, there may be a case that you want to keep this from being oxidized. Alright? You use a protecting group to shield this formal group. So if you use a strong agent without any protecting group, you oxidize these two ends. Now that you have protected this portion, what is left to oxidize? The primary alcohol group at the end. And so here you have a combination of a formal group and a carboxyl group at the end. Alright, again, when you use a protecting group, that is. And everything in the middle, as with the first two cases, remains unchanged. And the name of this, alright, in general is an alduronic acid, or simply a uronic acid. And the name of this uronic acid, if it came from glucose, is glucuronic acid. Alright. But oxidation does not only happen in the linear forms of a monosaccharide. And also, not just to monosaccharides, it could also happen to cyclic forms and even in disaccharides, but we will go to this later. I would first like to focus on this part, which is the formation of a glycosidic linkage. Alright, so here I am given two molecules of glucose, specifically glucopyranoses, because they have already enclosed to form a ring. So we have here two glucopyranoses, and one famous reaction commonly happening between two glucose units is that one anomeric carbon here, alright, I won't anymore review what the anomeric carbon means. It could target one of the hydroxyl groups here. Alright, one of the hydroxyl groups here. So in particular, this would actually target carbon number 4. I would first designate the numbers just to be very clear. 5, 6. Alright, so when you have something like this, this is carbon number 1, and carbon number 4 is the target of the anomeric carbon. What happens is that this one would form a bond with this, and at the expense of removing a hydroxyl group right here. And so after the reaction, what would happen is something like this. I'll draw it again completely. Unchanged, unchanged, unchanged. Still the same, still the same, still the same, same. And the only thing that we would now see is this one. Alright, so now there is a formation of a bond between the two, and the name of this is a glycosidic bond. Why? Because it is a bond that joined two glyco, meaning sugars, that join two monosaccharide units together. Alright, if you look at it, it's of the structure ROR, right? This is a carbon, this is oxygen, then another carbon. So that's why a glycosidic bond is also a type of an ether bond. If you're going to be very specific or technical with it, it's also an ether bond. Alright, so how do you name glycosidic bonds? For example, this is an anomeric carbon in the alpha form. Alright, alpha. I should have actually drawn this in alpha, so let's assume I drew it initially in alpha. Alright, that's my mistake. So anyway, it will become removed. So this is alpha, then this is number 1, and this is number 4. The name of this, as a result, is an alpha 1,4 glycosidic bond. So you would observe that here, the number beside the alpha or beta, depending on the anomeric configuration, is the number pertaining to the carbon, which is either alpha or beta. Alright, so we will have an example. We'll do that again here. Alright, actually let's do that now. So actually this is a molecule of sucrose, which is a combination of glucose here and fructose here. Alright, and this is carbon number 1 of glucose, right? This is the anomeric carbon of glucose, and it is in the alpha because it faces downward, and then this one is beta because it faces upward. Alright, and this is for fructose. Okay, I forgot that small carbon here. Right, so now it's complete. So now we have also carbon number 1 here, right? We have carbon number 1 here. So here, the glycosidic bond is alpha 1, pertaining the 1 referring to this one, and 1 beta referring to 1 here, and the beta of fructose. So this is an alpha 1, 1 beta glycosidic bond. Now finally, to end this topic, I would also like to mention that again, oxidation can happen in ring forms of the carbohydrates, and not just in monosaccharides but also in disaccharides, and that depends on whether we have the presence of what we call a free anomeric carbon. Again, I won't anymore elaborate what is an anomeric carbon again, but I will elaborate definitely what is a free anomeric carbon. And a free anomeric carbon is any anomeric carbon without a glycosidic linkage or a glycosidic bond. So for example, I'm going to highlight all the anomeric carbons here. Here, 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 and here. We've already gone through that. In this one, for sure, this is a monosaccharide. It's impossible for you to find a glycosidic bond there. So automatically, all monosaccharides are oxidizing. So this one is oxidizing. Alright? Actually, this is fructose. Alright? So one thing you may actually be thinking in the previous topic or in the previous video for carbohydrates is that if it's a ketone, just like in organic chemistry, it can't be oxidized. But the thing is, fructose, alright, be very careful. Fructose can be oxidized because when it closes to form a ring, it has a free anomeric carbon. So just to say that fructose cannot be oxidized because it's a ketone, that's incorrect. Because first of all, fructose can exist in the ring state and it has a free anomeric carbon. And another thing is that fructose can actually spontaneously isomerize to glucose, the aldose isomer of fructose, which is what we obviously see here as something that can be oxidized, alright, or something that is a reducing agent. So here fructose has the same property. In this case, we have a disaccharide. The name of this one is maltose. This is actually the same carbohydrate as this one. It is the product of two glucose units in an alpha-1,4 glycosidic bond, just as we have seen here. And here, the anomeric carbon is subjected to a glycosidic bond, so this is not free. This one is not free. But if we look at this one, the anomeric carbon at this particular glucose molecule is free. And as long as you have at least one free anomeric carbon in that carbohydrate, for sure it is oxidizing. That's why maltose, even though it is a disaccharide, even though it is composed of two glucose